Let's start talking about direct sums of modules. Given a collection, so let's say given for now a finite collection M1, M2, Mk, let's assume they're all R modules for some ring R, not necessarily commutative. We define a module called their direct sum. So we define a module M called their direct sum, M called their direct sum as follows. We first need to specify what M is as a set. So purely as a set, it's just the cross product of these as a set. In other words, the elements of M look like tuples, ordered tuples x1, x2, xk, where each xi is an element of the corresponding mi. I runs from 1 to k, and we need to also specify how this becomes an R module. This becomes a module via component wise. So this is the set and component wise addition and scalar multiplication. So what this means is when you want to add x1 through xk with y1 through yk, just add each component dot 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 xk plus yk on the one hand, and if you want to multiply by the scalar r times x1 x through xk is just rx1 comma rx2 till rxk, and all these hold for all R running over elements of the ring and for all xi, yi elements of mi, I from 1 to k. Okay, so this is what we mean by component wise addition and multiplication. So this is a keyword here. Okay, now it's very easy to check that this makes M into a module. So I leave that as an exercise. At the end of the day, every axiom that you need to check will hold because it holds in each component. Okay, so first observation here, easy observation, is that M is an R module under these definitions. Okay, so exercise. Okay, now this guy is called the direct sum. So here are some remarks. So M is called the direct sum of the mi's and is usually denoted by the symbol direct sum. So this is the usual notation for the direct sum mi, I ranging from 1 to k. Okay, M is usually denoted like this. Okay, another short remark here, one can actually define direct sums even for infinite collections of modules, not necessarily for finite collections. So I'll just state that quickly. Can also define something called the direct sum of an infinite collection. So now I ranges over a potentially infinite indexing set I. One can also define this notion, but the key thing to remember is that this turns out not to equal the product as a set. Okay, so if you have an infinite collection of modules, the direct sum is, well, it's actually a certain subset of the product. Okay, more precisely, it's that subset of the product in which only finitely many of the entries are allowed to be non-zero. Okay, so anyway, that's something that we won't encounter in this course. So for now, we will not worry about that. Okay, Okay, so let's just do an example of direct sum of modules. So easiest example is to take abelian groups. If I take my ring to be the integers, I can take any abelian group is automatically a Z module. So I can take the cyclic group of order 2 and the cyclic group of order 3. Okay, so this is all cosets. So what does this comprise? This is all cosets of the form A plus 2Z. Right? A running over the integers. So really there are two cosets, the odd and the even numbers. This comprises all the cosets congruent to 0, 1 and 2 modulo 3, and of course these are both R modules. So what does the direct sum now mean? It just means I take M1 direct sum M2, which is sort of the same notation as this, is, well, as a set it's M1 cross M2 with component wise operations, right? So with component wise, comp wise plus and scalar multiplication. So for example, if I took an element from M1 direct sum M2, so let's take the element what we would call 1 bar, which is 1 plus 2Z, comma 1 plus 3Z. So here is an element of M1 direct sum M2. So how do I perform addition? So let's say I want to add to this 2 plus 3Z. Then all I have to do is just add each component separately, and the answer is, well, it's 2 plus 2Z, which is the same as the 0 coset, and 3 plus 3Z, which is again the 0 coset. So here's the addition, for example. Okay, so scalar multiplication similarly. So this is M1 direct sum M2. So well, it's a set with 6 elements, and in fact you actually have encountered this before when studying groups and the Chinese remainder theorem. So for example, here's a good way to understand what this direct sum is. It's actually the isomorphic to the cyclic group of order 6. Okay, as Z modules, therefore Z mod 6Z I claim is isomorphic. So there is an isomorphism to this direct sum that we just constructed. Okay, and what's the isomorphism? So like I said, you have already encountered this. So recall what was called the Chinese remainder theorem in the context of abelian groups, and the map is the following: given any coset A plus 6Z, you just map it to the corresponding A plus 2Z and A plus 3Z. So given a number A modulo 6, you just map it to the congruence class of A modulo 2 and A modulo 3, and recall that this map was an isomorphism. Okay, so I'm sort of referring you back to this lecture, the Chinese remainder theorem. So recall phi was an isomorphism. So it's an isomorphism of groups. Well, they are both abelian groups in this case, so they are in fact an isomorphism of Z modules in our case. Therefore, of an isomorphism of Z modules. So in this case, the direct sum is nothing but well, we can identify it with the Z module Z mod 6Z. Okay, so so conclusion, Z mod 6Z is actually isomorphic to the direct sum. Okay, now let's do another example. So this is an example with Z modules. Here's a sort of a general example. So if R is any ring, so recall you can think of R as a module over itself by the left multiplication. Now let's just do the following. Let's take M1, M2, Mk to all be just R, okay, as a left module over itself. So I just think of all the MIs as just being R itself. So what I'm trying to do now to form the direct sum is, it's like I'm taking k copies of R. So what does the direct sum now become? So the direct sum of the MIs, I ranging from 1 to k. Well, by definition, this is just, as a set, it's just M1 cross M2 cross Mk. So in other words, it's k copies of the ring R itself. So this is k copies. Okay, so as a set I am just forming the cross product of R with itself k times. So this set is what we usually denote as R to the k, right? So this is the direct sum of R with itself k times is as a set R to the k with component wise addition and scalar multiplication. Okay, so this is again an example of a direct sum. Now let me look at direct sums in relation to homomorphisms. So there is there are some obvious homomorphisms that are important. So suppose I again have the same setting, I have M1 through Mk, which are R modules. Then observe that I have a map from each Mj. So let me take any one of these guys, and from that I have a map to the direct sum. Okay, what's this map? So let's give this map a name. Let me call it alpha sub j. This map does the following. If I have an element x in the module Mj, it maps it to the ordered tuple, which is 0 in all the other components, except in the jth component alone. So this is now the jth component. It takes the value x. Okay. So this is the map from Mj to the direct sum. So this is a well defined map, and as is clear because the right hand side has all component wise operations, it's clear that alpha j is a homomorphism, is a R module homomorphism. Okay, because addition goes to addition, x plus y goes to x plus y on the right side, and similarly when you multiply by R on the left side, it goes to multiplication by R on the right side. Okay, so alpha j is in fact a homomorphism, and what's more, alpha j is an injective map. Alpha j is injective. In other words, it's a one-to-one map. That's again clear because x maps to the sort of the tuple with x in the jth component, right? So two different things can't map to the same thing on the right side. Okay, so it's clearly an injective map, and so if you look at the image of alpha j, so consider the image of alpha j. So what's the image? It's, well, one way of saying it is you just take all tuples in which, so this is can be written like this, 0 cross 0 in all the components. The jth component alone, I take the whole module Mj. Okay, so that's the image of alpha j. Recall the image of a homomorphism is always is a submodule. So what does this map alpha j do? It maps Mj injectively, right? It's a one-to-one map, and instead of taking the entire direct sum on the right side, let me just look at this image that I described for you, image of alpha j. This is this set. So consider alpha j from Mj to the image of alpha j. Clearly this map is an isomorphism now. Okay, why is it an isomorphism? It was already injective, and since I have restricted on the right hand side to just the image, it's also surjective. Okay, so alpha j from Mj to image of alpha j is in fact an isomorphism of modules. So what that means is that in some sense, see, and recall that image of alpha j is a subset of the direct sum, right? This is a sub of the direct sum Mi. Okay, so the image of alpha j is a copy, is an isomorphic copy of Mj. Okay, so what we have inside the direct sum really is a copy of each of these modules Mi. Okay, and so sometimes one draws the following picture. So I have M1, M2, M3 and so on, Mk. The direct sum of these modules Mi is there. Now from each of these modules I have this map, what I am calling alpha j, right, or alpha 1 from m1 to this, alpha 2 from m2 to this, and alpha k from mk to this. So I have all these homomorphisms, and each homomorphism does the following. It takes the corresponding mi isomorphically to a copy of itself which sits inside the direct sum. Okay, and the way it sits inside is what we described right here. It's zeros everywhere else, and only in the jth component you keep mj as it is. Okay, so this is one way of understanding what the direct sum really is. Now let's talk about another sense in which the word direct sum appears, this notion, and this is sometimes called just to distinguish it from the earlier one, we sometimes call this the internal direct sum. Okay, so this notion is usually called internal direct sum. So I am just putting the internal within parentheses right now because soon we will see that for all practical purposes this internal direct sum is really the same as a direct sum in some sense. Okay, so we will make that precise, but for now let us keep this word internal to remind us that this is different from what I have just described. Okay, now what is this internal direct sum? What is the context? So what do I need for this? So I need a module M. So suppose M is an R module. So suppose M is an R module, and I have a collection of submodules of M. Okay, and Mi is a submodule of M for all I from 1 to k. Okay, so I have k different I have k submodules of my module M. Okay, now definition, we say that M is the internal direct sum. We say that M is the internal direct sum of the Mi of this collection of submodules Mi, I goes from 1 to k, if the following happens: if each element M belonging to M can be written as a sum, can be written as a sum M equals M1 plus M2 plus Mk. Mi is coming from the corresponding modules Mi for all I in a unique manner. Okay, so there are two parts to this definition. On the one hand, you can write it. In other words, there exists such a way of writing M, and there is a uniqueness part also, that this way of writing must be unique. Okay, so what does this unique mean? So let me just explain that a little bit more. Unique manner means if I can find another such decomposition, M1 prime plus M2 prime plus Mk prime is another such decomposition of M, or way of writing it into a sum, then in other words with Mi dashes all coming from the submodule capital Mi, then the Mi and the Mi dashes have to be the same for all I from 1 to k. Okay, so this is the definition. We say that M is an internal direct sum if every element admits a decomposition into a sum of Mi's in a unique manner. Okay, now let's now reconcile these two notions of internal direct sum and what I initially called a direct sum. So now observe that these modules Mi's, so when I define these modules Mi's, when I gave you the modules Mi's, I said they are all submodules of some ambient module M. right? So I have an M, that's my module, and inside M I have these submodules. So that's M1. Well, any two submodules at least intersect in the origin, I mean in the 0 element. So let's say, let's draw a better picture. So let's say that's M1, maybe this is M2, that's M3, and so on. So I give you a bunch of submodules, but a submodule can of course be thought of as a module in its own right. Forget the fact that there is an ambient module, a module which contains it. Just think of each of the MIs as just being modules in their own right. Okay, so view the MIs as modules in their own right, and when you do that, we can then form their direct sum. Okay, so this is the direct sum that I talked about at first, sometimes called the external direct sum as opposed to the internal. So let's form their direct sum. I equals 1 to k. Okay, so recall what is this as a set. This is very different from the elements of this external direct sum are not going to be elements of M or anything. Okay, they are in fact tuples of elements, right? Remember, this is just as a set, it's the cross product M1 cross M2 cross M3 dot 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 till Mk. So this is some new set. It's a module in its own right, again the direct sum. Okay, so we can form this new object, the direct sum. But what's interesting here is the following, that now consider the following. So maybe to phrase this properly, let me just say, let Mi be so let me say B submodules, okay, I from 1 to k. So this is a collection of k submodules of an ambient module. I can view those as modules in their own right and form the direct sum. Now from this direct sum, there is always a homomorphism that I can define to my module M. Okay, so consider the map phi from this direct sum. So what is this map going to be? Well, a typical element here looks like this, M1, M2, Mk. So what I'll do under this map phi is to just send it to the sum of these elements. Okay, so this is for all MIs coming from Mi. Okay, now this map I can always define whenever I have a collection of submodules, and it is very easy to see again that this map phi is in fact a homomorphism. So phi is a R homomorphism, where R is the ring over which everything is a module. Check, this is again from the fact that the direct sum has all component wise operations. Okay, so phi is a R homomorphism, that's very easy. Now the key point here is that observe that if these submodules Mi, if the ambient module M is an internal direct sum of these submodules, then what does it mean? Well, it means the following. If you go back to this definition, if M is the internal direct sum, then every element of M can be written as a sum of MIs. Okay, what does that mean? It means that this map phi which I have just defined, this map is surjective, right? Because every element of M has one such decomposition. Okay, every M can be written like this. Now, so phi is surjective is really the first part of the definition, and the second thing says everything has a unique such decomposition. Okay, what does that mean? Well, that just means that phi is injective. Phi is a one-to-one map, right? Because given any element on the right, I can only find a single tuple M1, M2, Mk such that M can be written as their sum. Okay, so what this means is that more or less by definition, observe that note M is the internal direct sum of the submodules Mi 1 to k is the same as saying that this map phi which I just defined is an isomorphism. Phi is an isomorphism. Okay, isomorphism of R modules, of course, everything is over some ring R. Okay, so what this means is that this notion of internal direct sum, right, if M is the internal direct sum, in some sense it's isomorphic to the external direct sum of the MIs. Okay, so that's sort of why one after a point stops making this distinction between internal and external. In some sense it's really the same notion. Okay, now let's look at this internal direct sum or direct sum now in the special case of where you only have two submodules. Okay, so this is this is something which comes up very frequently. So let's just take two submodules. So let me look at suppose M1, M2 are both submodules of M. Submodules. M is an R module as before. Then let's look at M1 direct sum M2. So what does it mean to say that M is the internal direct sum of M1 and M2? Okay, so M is the internal direct sum. So we will now denote it like this: M equals M1 direct sum M2. In other words, it's the internal direct sum. So this is now we'll just use the same notation for the for both direct sums, internal or external, i.e. in other words M is the internal direct sum of these two submodules. Okay, so then observe, then note the following: M is the internal direct sum can be written as follows, rephrased as follows, if and only if M1 plus M2, so two things should happen. One, the sum of these modules should equal M. Okay, so recall we talked about this general construction of submodules. This is the usual sum of submodules. Okay, and what was sum? Sum was supposed to be the following: you take the union of those two guys, M1 and M2, and look at the smallest submodule, the submodule of M generated by the union. Okay, that was the definition of the sum. And we had, back when we talked about this construction, we also said the sum is, what are elements of the sum? They are nothing but things of the form M1, little m1 plus little m2, where m1 comes from capital M1 and m2 comes from capital M2. Okay, so go back and look at the video on sums of submodules. So here are two conditions. Number one, that the sum, the ordinary sum of these two guys should be M, and property 2, the intersection of these two should be just the zero submodule. So I claim that if these two properties are satisfied, if these two properties are satisfied, then M is just the internal direct sum of M1 and M2. Okay, and conversely. So let's prove one direction, the other is sort of similar. So let me prove the reverse direction. If I know that M1 plus M2 is M and M1 intersection M2 is 0, why does it imply that capital M is the internal direct sum of M1 and M2? So let's prove the converse. So we need to show that given any element M in M, need to show that M can be written as a sum M1 plus M2, M1 belonging to, so Mi belonging to Mi in a unique fashion. Okay, so let's prove this. Number one, M can be written like this because, so firstly observe, since just the ordinary sum of M1 and M2 is all of M, this means that there exists M1 in M1 and M2 in M2 such that M can be written as their sum. Okay, this is again from like I said, from that video on sums of submodules. Now let's prove the uniqueness that comes from the second part of the hypothesis. Okay, so let's show uniqueness. So if I can find another such decomposition. So let's say I have one such and another one. Then let's do the following. Let's subtract. Let's pull the m1 dash to one side and m2 to the other side. So this is the equation that we now get, and now we make the observation that the left hand side is an element of m1, the right hand side being a difference of two elements of m2 is an element of m2. Okay. So here's an element which lives, so whatever you call this element something x maybe. Now this element x lives both in m1 and m2, which means that x belongs to their intersection, but which by hypothesis is just 0. Okay, so this means x is 0, and x is 0 automatically means that these two guys are equal to each other, right? So what is the conclusion from here? It's completed. This means that m1 equals m1 dash, m2 equals m2 dash. Okay, so that completes the verification of the converse. So let me just say this is similar. So let me just leave this as an exercise. Okay, so this is the case of two modules, two submodules m1 and m2. Okay, now this is sometimes called a pair of complementary submodules when you have two modules which whose direct sum is the whole. Yeah, and we'll talk about them in a later video.